other businesses. We do a lot of work trying to support existing businesses grow. So, for example, we've created a CyberNorth web page, cybernorth.biz, and we use that to disseminate information about joint events, etc., etc. But we're also creating a shared area, an intranet, where businesses can come together and collaborate to try and win business. We're creating and developing new business. We're trying to start a cybersecurity innovation center with Newcastle University and with Accenture, with a view to creating a new innovative businesses in cybersecurity. And that will either create those businesses or will create highly skilled professionals who the other businesses can't accommodate. What I'm trying to do is to address the skills shortage in the region. I think this is something that all industries are facing now, struggling to get the right people into the roles. Yet my experience tells me that we don't actually have a skills shortage, we have an experience gap. There are plenty of skilled people, but there are not enough people with business skills to be able to fit into the businesses that we have. So a bit about the Northeast. We've got 70 or so businesses delivering cybersecurity services in the region, right from Berwick in the north down to Tees Valley in the south. We have some large consumers as well of cybersecurity services, such as Nissan, Sage, North P&I. We've got some active public sector organisations, DWP, HMRC, the National Health Service, BSA. So some of the big public sector businesses are really running out of this region. They're very strong in the public sector of this region. And of course, there's the 12 local authorities as well. We have about 5,500 academics working in cyber security at the moment, either pre-graduation, postgrad, etc., masters, etc., like that, PhD. So across the 5 universities, so there's a lot of talent there. There's about 1,000 employed professionals in the sector, working across the sector, across the region. And so we have about 2% of the businesses of the country in the Northeast, and about 3% of the population. So we've still got some way to go in order to catch up. Okay, hand the next slide, please. So as I said, we're running Cyberfest throughout September. This is the 5th year that we've run this. We've got 17 events running throughout September. This is the 13th of them. I've got a couple, 3 more this week, culminating in our season finale at the Brinkburn Brewery this Thursday between 6 and 8. You're welcome to come along. Got a couple of talks, one on low code, no code, and the other on SEAMS. But we're also showing the art competition, where we've run for the last 3 years, a collaboration between CyberNorth and Creative Fuse Northeast to look at the way that art can be used to highlight cybersecurity. So there'll be some demonstrations, some performances, and there'll also be a free drink for you if you come along. So please, if you get a chance, come along on this Thursday at Brinkburn Brewery. Next slide, please, Hans. Okay, to get us into the meat of this PRIFF workshop, there's really a couple of things that are going on in the background that I really wanted to talk about, just a brief intro. First of all, there's the finance sector and the fintech sector, and then there's the GDPR regulations. So this is a highly complicated market. Indeed, we've got one of the events in Cyberfest tomorrow. So I'm not sure whether that was me or you, I've no idea, but there you go. So there's a huge amount of requirement for data. That previous slide shows that some of the many applications that data be required. But the problem with finance is if you're going to steal anything, you might as well steal money, because it's the easiest thing to spend. You can always use money anything. Money's the best thing to steal because you can spend it anywhere. And there's a drive, significant drive for anonymity in the data that we have, and I guess that's what today is all about. Yeah, sorry. Can I have the next slide, please, Han?
Okay, so the first was around the huge opportunity for the usage of data, and the huge pressure to have that available for businesses to make value out of, and clearly the need to anonymize that or pseudo-anonymize that is enormous in order to protect yourself against the second thing, which is really GDPR, the General Data Protection Regulations, which have been around for some time now. A huge piece of influential and powerful piece of legislation, and I think it's really done for data what the health and safety legislation did for safety on building sites, etc., etc. It's really brought it to the fore of people's thinking. A bit of teeth, a bit of nudging, fines here, but general persuasion has been great. But it's a hot item. Legislation will continue to change as the use for data increases, and it's a truism that legislation cannot keep up with the change that's going on within technology at the moment. So you may have heard of 6 degrees of separation, where everybody in the world is connected to each other through 6 other people. I wonder how many pieces of data is required to get people back to know something about whoever it is that you're talking about. Perhaps 5 or 6 pieces of data that you need, and you'll know everything about everybody. Okay, next slide, please, Hans. Right, okay, so this is what today's about. Deep learning technology is driving a dramatic shift in how financial institutions run their businesses. However, as we've just described, it brings serious privacy risks, from sensitive customer information leakage to ethical principle violations. Legal regulations in the GDPR are also emerging to restrict the way financial institutions use customer data, and in this context, the traditional centralized machine learning technology can be problematic because it needs to aggregate all data into a central server to train a model. So that's what we're going to talk about today. And next slide, please. Thank you very much. And I've got 2 speakers, Han, who you've already met because I've been talking to him for some time, and Dr. Zhilong Zhao from the Technische Universität in Delft. Next slide, please. And this is the format today. So I think we might be running a bit behind due to technical issues, although it looks like we're right on time. Han, over to you.
Good afternoon, everyone. Welcome to the first session of this brief workshop collocated with the CyberFest event. I'm Han Wu, a research associate from the School of Computing in Newcastle University. The topic of this first session is called Federated Learning in Financial Services. So through this presentation, I wish you can get a brief understanding of what federated learning is, how does it work, and why is it necessary in financial services. So machine learning technology is now increasingly being deployed in the real business of financial services. According to the survey, the joint survey conducted by the Bank of England and the Financial Conduct Authority in 2019, over 2/3 of the investigated financial firms have already deployed machine learning applications in their real business. Such business include banking, investments, payments, retail lending, and insurance. Especially for the insurance business, those firms totally rely on machine learning technology to make decisions. I'd like to roughly introduce the general stages of the machine learning pipeline. There are basically 4 stages. The first and the most important one is the data preparation stage. You're gonna need the overall machine learning is a type of data science technology. You're gonna need to build models based on large amounts of data. Normally, we are split the data set into training data and test data. Then, for the next stage, we construct a machine learning model. We train this model based on this training data until it reaches convergence. Then we validate the performance of this model on this test data set. So if the performance reaches an acceptable level, we can deploy it in the real business to see how it works. So these are the 4 fundamental stages of machine learning. I'd like to say a few more words about the data, because this is where the notions of privacy lies. Especially in financial services, the financial firms usually controls the sensitive and personal information of customers, which are where the privacy comes from. Fundamentally, there are 3 types of data used in financial services. For the first is structured data. This type of data is usually highly organized, and the data objects in this type of data usually have fixed meaning. A typical example of such kind of structured data is tabular data, usually seen in those standard financial database. Each line in this table represents the records of a particular customer. The second type of data is called semi-structured data. Those type of data is usually less organized than the structured data, with some hierarchy present, such as tags and fixed predefined structures. The typical examples can be the web pages, such as a HTML file, or particular type of data files, such as JSON and XML. The third type of data is called unstructured data. This type of data is least organized because the information does not follow a pre-existing data model. For typical examples include images or text. For example, in an image data, the pixels in the image does not have a very fixed meaning. We're gonna need analytical techniques to transform the image into a meaningful information. So these are the most commonly seen three types of data in financial services. And among them, the structured data, or so-called tabular data, consists more than 80% of the machine learning use cases. So throughout this workshop, I'm gonna use the examples of tabular data to tell these stories. About the problems, I'd like to talk about the constraints of deploy and develop machine learning technologies in financial services. Those constraints mainly come from two sides. First is a constraint of insufficient data. As I said before, machine learning is a type of data science technology. So its performance highly depends on the data you use to train the model. The insufficient data problem usually comes from three aspects: the insufficient amount, insufficient diversity, and the insufficient dimension. On the other hand, there are also privacy concerns for those financial firms, usually constrained by the data protection regulations such as GDPR, and also financial companies usually have their concerns on the commercial confidentiality of their data. And if companies want to connect sufficient data to train a model, there is a risk of data breach. I will use some very concrete examples to elaborate this problem. So for case one, there is a bank, we call it Bank A here, who wants to train a machine learning model to do the loan prediction. So this table is the data what we got. It's a tabular data. Those in the blue frame are called features, and they are the input for the machine learning model. And this long column are called labels, which are the outputs of the machine learning model. So basically, we expect the machine learning model will take those features as input and make predictions for the customers, whether they are got a loan or not. So for simplicity, we call those customers who has loan labeled as negative. We call them negative customers, and on the contrary, we call them positive customers. So in this particular case, we assume that Bank A is a startup company and it doesn't have sufficient data stored locally. And more specifically, most of its customers are negative customers. So if Bank A tries to train a machine learning model based on this kind of data, the model will have poor performance or even cannot be trained. It's easy to understand because for Bank A, the machine learning model only sees the data of negative customers. It does not know what the positive customers look like. To solve this problem, you can use synthetic data. Now there exists some open source public synthetic data sets released by large companies, but there's always a problem with synthetic data. For example, it can be the data formats on the synthetic data can be incompatible with those on the bank A's. And also, synthetic data is difficult to prepare. You're gonna need a large real data set to generate synthetic data. There is the last and the most important one is the utility problem. If you use synthetic data to train a machine learning model, then the performance of the model could never reach the performance of the model trained on real data sets. So that is a performance penalty. Another solution intuitively is to connect sufficient data from other sources, if there are any available. We assume that there are other two banks, B and C, who stores the same type of data, but they got more positive customers to improve the diversity of the data set stored on bank A's. So those banks may find a trusted technology company and send their data to this company to train a machine learning model. In this case, those data are transferred to a third-party company, which can cause those privacy concerns I mentioned before, because all of those data contain very sensitive and personal information, and it's very risky for those banks to transfer those type of data from one place to another. So researchers and scientists come up with a distributed solution for this problem called Federated Learning, which allows each bank to train a submodel locally and shares only the parameters of the submodel. So in this case, by applying the Federated Learning paradigm, each bank A, B, and C will train a machine learning model locally. And then they send only the parameters of the model to a trusted parameter server. The parameter server will aggregate these models based on some averaging algorithm to generate a global model. Then it releases this global model to all the three banks for the next round training. So this process will take a few rounds until this global model reaches acceptable performance on all of those banks. So in this distributed federated learning paradigm, each of the bank manages to keep their data stored locally, and they share only the parameters of the model. The parameter server cannot see the data from those banks. It only receives the parameters. So this perfectly avoids the data breach risks. In the previous example, if we see the training data as one entity, then we can see the tabular data is horizontally split. We call this horizontal federated learning, which means bank A, B, and C, they share the same feature spaces. They all got data like age and income as their features, and the same label space. They all got loan as their labels, but they store data for different groups of customers. Then, in practice, there is also another case. For example, we assume there is a bank D who has sufficient amounts of data, including those positive and negative customers. However, since it got a limited number of features, it has only age and income information. just for a simple example of those customers, and that might be insufficient to train a utilizable machine learning model. So the Bank D expects to increase the dimension of this data set to include more features. And meanwhile, there is a fintech company who holds different features for the same groups of customers. Those different features can be deposit and shopping in this case. So these features together can improve the performance of the machine learning model. And Bank D would like to cooperate with fintech company to build a machine learning model trained on the joint data set. We call the solution the federated learning paradigm can perfectly solve this problem. We call this solution as vertical federated learning. So this is a general process of vertical federated learning. This green neural network is a model we want to train, and is split into 3 parts. The fintech company and the Bank D, each of them holds a bottom part of this neural network model. They input their data to this model until a middle layer. Then the intermediate outputs will be sent to a top model server, which receives those outputs and forward them to the end of this neural network. And the output will be the predicted neighbors. Then the server will calculate the loss between the prediction and the labels here to update the whole model. This process will also run in a couple of rounds until this entire model reaches convergence. So in this vertical federated learning paradigm, the fintech company only sees part of this model, so does Bank D. And the top model server will not see any of those data stored on them. Bank D also cannot see the table data stored on fintech company, and neither do the fintech company, or the other way around. So this here is a comparison of the horizontal and vertical federated learning. The first difference comes from the data characteristics. In the horizontal federated learning scenario, each of the participants holds different individuals, but they share the same feature space, same attributes actually. But in vertical federated learning, the different participants share the same group of customers, but they have different feature space. And for the second difference comes from the number of participants. In practice, the participants are in horizontal federated learning can be up to hundreds or thousands. This is imaginable because you can imagine that there are there are hundreds or thousands of financial companies. But they store data for different groups of customers. While in vertical federated learning, the participants are usually less than 5, because it's not common to see a feature space larger than 100 in real world cases. And the third difference comes from the model structure. In the horizontal federated learning paradigm, each of the participants holds the same type of identical machine learning model. When the training process finishes, each of those participants get the same global model in the end. But in vertical federated learning, each of the participants only holds part of this global model. So none of them knows what the global model looks like. The fourth difference comes from the messages exchanged. In horizontal federated learning, the participants communicate with each other, also the server, only on the model parameters. But in vertical federated learning, you need to transfer the intermediate outputs of the model. So this directly causes the last difference, the communication cost. In horizontal federated learning, in each round, you have up to n exchanges in every round, where n means the number of the participants. But in vertical federated learning, the communication cost within one round can be significantly higher, because you have to input each intermediate output of your record on your data set into this neural network. And those intermediate outputs will be transferred from those participants to the server. So that is a very high communication cost. And that's all of this first session. Thank you for your attention. Now we start the discussion session.
Could you go back to this communication cost page? So you said which one have the more cost, communication cost? The vertical one.
Yeah, the vertical one.
And the reason? It's because it's changed the data, or
Yeah, it's from the perspective of each participant. So in the horizontal federated learning one, for each participant, within one round, you only need to upload your model parameters once. And that is different from the vertical one. In vertical one, within one round, you have to for each record on your data set, you have to transfer the intermediate output to the server.
yeah, but I mean, how you define one round, right? So because for your vertical app file, each mini batch you need to upload this data, right? But for the horizontal app file, you actually need to train. After training, you upload the weights, right?
Yes. For the concept of round in horizontal FL, I think it's where within one round, all of the participants need to upload their parameters to the server at least once.
Yeah.
But in vertical FL, the concept of round means you have to go through the neural network with all of your records in your dataset. And
What I mean is, like, if you go through all of your data to be counted as one round, I mean, then maybe their communication cost is maybe even the vertical one should be higher, no?
Yeah, the vertical one is higher.
Okay. Okay, maybe I misunderstood before. Yeah, okay. It's clear now.
That's all. That's okay. Any other questions from any of our in the room?
Yeah, I have a question. I don't know if they can hear my thing again. But I think it would answer that maybe. So about the creation of synthetic data. In order to create synthetic data, don't you need like a model to create it from? So it seems like a chicken and egg thing, right?
Yeah. To create a synthetic data, you have different approaches to generate a synthetic data. Most advanced approaches rely on machine learning models to produce. But before that, you have other options to generate a synthetic data.
Yeah, but the synthetic data will again be of the following features and labels here. So how do they get this data?
That's why I said synthetic data are usually released by those large companies. They already have a large amount of real data, so they can build a synthetic data generator based on this.
And they share it with other companies.
Yes. So you need to have access to the real data first.
Okay, so you have the real data and you put some noise or something like that, and you share it with others.
Yeah.
Okay, makes sense.
Yeah. So about synthetic data, Dr. Zhao will give, for the next session, Dr. Zhao will give a presentation particularly on this topic. Yeah. Any other questions?
Good afternoon, everyone. Thanks for joining this session. My name is Zilong Zhao. I'm a postdoc here in TU Delft. Today, my topic is distributed generative model for tabular data. You can see my screen, right?
Yes.
Okay, cool. So this talk consists of two parts. They are from two of my papers. First is a generative adversarial network for tabular data. Second one is federated learning for tabular GAN. So in case some of you may be interested in the details, I put the titles and the link of the paper here. My talk today will mainly focus on the background and the result. So I will skip most of the technical details, but of course, if some of you are interested, we can discuss in the discussion part. Okay, let's start. The first is conditional tabular generative adversarial network. So why we need GAN? The reason is because the data accessibility is limited. So as we can see every day, we generate a lot of data, but very few data are analyzed and used. And with the, as Phil said, right, with the regulations such as GDPR, it further limits the data accessibility and shareability. Therefore, some banks and insurance companies came to us. This is also why I started this topic, and they want to use synthetic data to replace original data. And GAN is one way to do that. Yanni LeCun, the Turing Award winner, he said that maybe 4 or 5 years ago. So generative adversarial networks is the most interesting idea in the last 10 years in machine learning. I mean, I know now the more like hot topic is diffusion model is a new hot topic in generative model, but GAN still hold a lot of state of the art in many jobs. So we will talk GAN today. So let's see what GAN can do. The first most famous GAN application is style GAN. I think it's a work from NVIDIA. So it learns from real human face and can generate synthetic human face. So all these faces here are not real human face. They are synthetic, but they are realistic. So yeah. Then here is the problem, right? So GAN is first started for images, but it cannot directly apply it for tabular data. Why? So here we can see images are the metrics with continuous value. So for example, if it's a RGB image, each pixel runs from 0 to 255. If one pixel changes, for example, I don't know if you can see here, if one pixel changes from, for example, 62 to 63, it doesn't really influence this image. But for the tabular data, there are continuous and categorical columns. So for categorical column, if one number changes from category 1 to category 2, it totally changes the meaning. So the discontinuity of tabular data prevents us directly applying image GAN for tabular data. So here I show some motivation cases from our paper. So we first show some columns original distribution and comparing to the synthetic data distribution from the state-of-the-art tabular GAN algorithms. The first figure shows the mortgage column in the long data set. I think Han also showed this long data set. It's a public data set and it's quite easy to use in the tabular data analysis. We can think about this mortgage column, right? For a person, if we have all his information and if it has mortgage, what's the education level, and in the end we choose if we gave the loan to him or not, or to her or not. So we think about this mortgage for a person, it can be 0. That means this person doesn't have any mortgage, or some number. But if it has some number, it won't be $1 or $2, right? It will be several hundred, thousand, or even more. So there's a clear discontinuity between the peak. Here is a peak at 0 and other parts. So it's also can't be negative. So apparently none of the state-of-the-art tabular GAN can learn this distribution. Second figure is the transaction amount column in the credit card data set. So we can imagine that what we show here is the density. So it's the CDF. What we can imagine that most of the transaction number is less than, say, $200 or $300 because it's just the daily shopping or pay for meals. It wouldn't be large number, but still one can buy a house or a car, right? So it can be extremely large. So we call this type of distribution long tail. So that means most of the occurrence at the beginning, but the distribution can be very long. And apparently none of this state-of-the-art can recover this distribution in their synthetic data. Actually, they are far from recover that. And the third figure shows the working hours per week for the adult data set. So we can see most of the people works 40 hours per week, but there are also some people works 20 hours per week, or 50 or 60 hours per week. So what the challenge here is that in this column, there is one dominant number. So if we don't deal with that, the GAN algorithm will be difficult to learn other value except this dominant value. So before we in GAN training, they call it a mode collapse, but with the new laws proposed in this area, it is more stable than before. But if the training data is very biased, still it can't really learn that well. Therefore, we propose, I think I will skip most of the content here. So I just want to show here, we propose tabular GAN. We add an extra auxiliary classifier. We also propose new losses to this training to make it more stable. And also we propose also new feature engineering. So one thing for tabular data is that in tabular data, the original data, it contains many information, but actually it doesn't really show in the, if we directly gave this data to the GAN, it can't learn that. So we need to use the feature engineering to really encode this pre-knowledge into this encoded data. So it can show, for example, if it's categorical column, we will use one hot encoding to encode it. And for the continuous column, we use this here, actually something called variational Gaussian mixture. We encode it. And so we can show the correlations directly in the encoded data. This is one thing we did. And also for a long tail distribution, we also proposed something to transfer it before we learn it. And also to counter the imbalance column, like we show in this hours per week, we propose a way to how to construct a conditional vector and like training by sampling, but by the log frequency, not the original frequency. So by all of that, so we'll achieve that. Opposite type GAN, you can see for the mortgage in long data set, we recover clearly this peak and some other continuous value. And for this density, it's almost perfectly recover this transaction amount. And also for hours per week in adult data set, it's it's already learned its dominant value, but it didn't ignore others. So that is very good. Yeah, so I think for the first part, I will stop here and I will go to the next part. Is also the topic today, right? How to federated learning for tabular GAN. First of all, here also, why we need federated learning for tabular GAN. For think about a scenario, there are several hospitals. So each of them contains the patient records. All of them want to have more patient records to do the data mining, but none of them can share their data, right? Data, like patients' data is extremely sensitive. Therefore, they want to train a data synthesizer together. And this is what federated learning can do. So in the federated learning, clients can contribute their data to train a global model and do not share the data with other clients and servers. So after federated training, federated training, tabular data synthesizer, all the participants can use it to generate data, and then it can use for the local, for example, as a data augmentation. So here I summarized 3 reasons, but of course you have more. So the data sources are not centralized available. Private data are sensitive to shared to a third party. And some data sharing are not permitted by law. Okay, so after checking the reason to the federated tabular GAN, let's see what is the challenge here. So here it involves a little bit of technical details. I will try to make it as clear as possible. So when we encode the continuous column in tabular GAN, current state of the art all uses an algorithm called the variational Gaussian mixture to approximate this continuous column distribution and encode the column. For example, here in this figure, this beta, like the length of the beta, indicate how many Gaussian mixture we got for the data for this one column we estimate. For example, here it has 4 mode. That means we have 4 Gaussian mixture. So in the centralized GAN training, this variational Gaussian mixture proves it can really improve the training of GAN. But in federated learning, each participant has different data distribution. Therefore, their estimated Gaussian mixture can be different. For example, when I apply this in my local data, I can have 5 Gaussian mixture, but others can have 3 Gaussian mixture. Then this length of beta is different. And then in the end, the encoded data length is different. And in the horizontal GAN training, right, if your input-output layer is different, then you can't merge your model together. So we need to solve this problem. And of course, we need to solve this problem in a privacy-preserving way. Otherwise, we can't use federated learning. Then how to unify the encoder is a problem, and a global initialization is needed. So here we show a case. That is, what if we do not have a proper initialized global encoder for one continuous column, right? Since different clients can have different Gaussian mixture. We imagine a scenario that we initialize the Gaussian mixture in the server instead of in the client. So in the end, then we will have a uniform like a Gaussian mixture encoder, and then we dispatch to all the clients, right? In that case, we don't have this problem. But if server only contains 1% of global data, as shown in this figure 2, in the end, the data synthesizer figure 1 is the original distribution, okay? And the figure 2 is what server have, is only in the tail, this part, they have only 1% of the data. So the final data synthesizer can generate the data like in this figure 3. You can see it's very far from the original distribution, right? And if there are 100% data in the server side, then you can have a very good like a global encoder for this column. Then the final data synthesizer can generate the data like in figure 4. And apparently it can like recover most of the data distribution. Therefore, in our paper, we propose a privacy-preserving way to initialize the global encoder using the data from all the participants, and that can enable the FL training for tabular GAN. I think I will skip this part, like how in detail it's do. In general, it's everybody doesn't really share their share their encoder, but share their data distribution. And in the server, we will fusion this data distribution, and we will have a global distribution, and then to encode for each of the column. Yeah, okay. And another contribution here is that also how we evaluate the contribution of each client, right? We need to have aggregation weights for the horizontal federated learning. And before, for this image federated learning, what they use is the number of data and also the label frequency, because for image, if it's not multi-label case, it only have one label, and they use the label frequency of the local data, so they can calculate the distance with the local and the global. But for tabular data, it's difficult because each column have its own distribution, and we can't only like calculate that according to one column. So we propose a way to calculate that. We use the JS divergence for categorical column and the Waterston distance for continuous column. And also we consider the number of data. So we use all these factors together to calculate this aggregation weights for the tabular GAN. In the end, so here, in general, what I want to show is you can see the model really converges. And we also did an ablation test, like if we don't use the component we proposed, it works relatively worse than everything is combined. So this is my talk today. Thanks for listening. And if you have questions, we can discuss now. Thank you.
Okay, sorry, I've got a question. I don't really know whether it's relevant, but you start off by saying that only 0.5% of data is analyzed. That seems quite a high figure to me, but we'll put that to one side. So have you any thoughts on how much data we need to analyze in order to have a high degree of certainty? And will your work actually increase the amount of analysis done, or will it just make it more anonymized?
Sorry, I may not 100% got the question. So how much data?
Yeah, so how much, so we're saying that 0.5% of data is analyzed at the moment.
Oh, yeah.
Yeah, so how much data do you think we need to analyze in order to have a high degree of certainty that the data is, what it's telling you is accurate?
I would say as much as possible.
Yeah, so do you think the work that you're doing will actually increase the amount of data that's analyzed, or just make it much easier to analyze the data?
Yeah, I think my work is to make it much easier to analyze the data. So the case when I start this study is because there are companies, they come to talk with us. They have a branch all over the world. For example, in China or in UK, in India, in other parts. But each country have their law, like the data cannot cross the frontier. So that means if like in the headquarters of Amsterdam, they want to analyze the data from India and they can't. So then they think, okay, maybe we can use the synthetic data and we learn the correlation, we learn the distribution, and then we can solve this owner issue. I think that this work is makes the analyze much easier, especially like if you want to this some institution collaborate with others, but actually it can also use as data augmentation. So original data I can think about, they are like some point in a sparse space, right? And if we learn this, we train this GAN, and when it's generated, it can normally impute this distance, like this space between different data point in the space. It can also use as a data augmentation. Yeah, but I think it mainly works for make the shareability easier. Yeah.
Thank you.
Hello. I have a question apart from the GAN part.
Yeah.
Before you start training, you're gonna need to distinguish the continuous column from the category ones, right?
Yeah.
So my question is, are there any rules to distinguish them? Because when I dealt with some tabular data, I met this type of problem. Let's take the column named education years as an example. It's actually the educational years of the customers. So it can range from 1 to 20. It can be seen, can be regarded as a continuous column, but actually different years of the education represents different education levels. So in some cases, actually in others programming codes, I saw them, they treated it as category columns. For example, one year represents a lower education level, and the longer years it takes, the higher education level it is. So is there what is the difference if we treat it as a continuous or category column? Would it further results?
Yeah, this is actually a good question, because when we start to like work on that, we also need to like artificially define that. So it's quite subjective. So this is the rule we use now. So for education, I think you can use categorical or continuous, but I actually maybe prefer it as a continuous one, because the 10-year and 11-year and 12-year, they actually have they really like it express, because 10 and 11, they really express some like relation, right? But for some really very like categorical column, right? For example, its gender is male and female, then, or you have some category, it has maybe 4 or 5 category. And if you only use 1, 2, 3, 4, 5, you actually artificially gave the distance between them, because the category 1 and the category 5, it doesn't really meet far than the category 2 and category 5. So in that case, I would say that is definitely categorical column. But for the number of years of education, I would say it should be continuous. But I mean, if this also depends, if you really have few number, it can also be categorical. But I think I will like prefer to deal with that as continuous. Yeah, I think it depends if this really the number have the meaning. It have this ordinal meaning, right? Otherwise, I think I will deal with that as categorical. But I mean, like, I understand what you mean. I didn't really have a script to automatically decide for me. Yeah, I need to like really know the meaning and decided that. Yeah, this is also I think something we can improve is because if we need to like manually configure that, it's also take some times. Yeah.
Okay, thanks. Any of you have questions? Any others online? Do you have any questions? Okay, so thanks for the presentation, Dr. Zhao. And we can go to the last session of this workshop. For the last session of the brief workshop, I'd like to present on the topic understanding the privacy risks in data synthesis and federated learning. So I'm going to stick to some use cases to elaborate those privacy risks and understand how the most advanced research conduct such kind of attacks on federated learning or data synthesis technology. So through the last two sessions, we got some knowledge about synthetic data and federated learning. Both of them are designed to be privacy-preserving technologies, but from different perspectives. So by data synthesis, you provide synthetic data instead of the real data, which which this way keeps the real data or real original data secure, and then the synthetic data can be used by other researchers or engineers to build models or do some data analysis on it. And for federated learning, it's a distributed machine learning paradigm, which allows the participants to train a machine learning model together without exchanging their data set. In both technologies, the real data set are kept securely by their owners. And so the risk of data breach is significantly reduced. But however, there are robustness challenges and various kinds of inference attacks. The definition of inference attack is that an attacker, there exists a malicious attacker without directly accessing the real data, manages to infer the sensitive information of the real original data with very high confidence. I'd like to first introduce the inference attacks on data synthesis technology. The first is a membership collisions attack. In this attack, the researchers assume that there exists a published synthetic data set, as here the yellow one. Oh, where's my mouse? Sorry. Okay, the yellow one on the right represents the synthetic data, which is open to the public. And this synthetic data is built on the basis of this real dataset D, which is securely kept by its owner. But since you use some data generating technologies like GANs mentioned before to produce this kind of synthetic data, so there might be an intersection set between those two, which means those records are they are identical, but they exist in both of those two data sets. So given this condition, if there is a malicious attacker who has access to this synthetic data set, and also the black box access to the synthetic data generator, then there is a possibility that this attacker can infer which records belong to the intersection with very high confidence. Actually, in the literature, in this literature, the authors reached over 80% confidence in the end. This means, given any records in this synthetic dataset, this attacker can infer whether this record belongs to I or not, this intersection. And then this malicious attacker manages to know which part of those data set are from the real ones. So this is called this membership collisions attack. Another type of inference attack on data synthesis technology is the property inference attack. This is under the assumption that the data generator is released instead of the synthetic data itself. So everyone can access this synthetic data generator to produce synthetic data as their need. And the condition to trigger this type of attack is that given the attacker black box access to this generator. In this example, we assume that in the real data set, it contains this kind of property information. 30% of those records are male. Then this synthetic data generator, which is trained on the basis of this real data, is vulnerable to those attackers. In this paper, the authors manages to infer this male and this gender proportion information based on black box access to this synthetic data generator. In the end, the attacker can infer the information that approximately 32% of those records are male, which is very close to what the situation in the real ones. So this is called the property inference attack. About the inference attack on federated learning, I'd like to introduce two attacks on horizontal FAR first. The first one is membership inference attack, which is very close to the previously mentioned membership collision attack. This is under the assumption that there's a malicious participant in the HFL system. Let's say bank A, B, and C cooperate with each other to train a machine learning model using the federated learning paradigm as an example, just like the example in my last presentation. So given the white box access to the model, which is reasonable because in horizontal federated learning, each of those banks knows actually what the global model looks like. So in this type of attack, the attacker manages to infer the existence of records in the training data with very high accuracy. Actually, according to the results presented in this paper, if the server is the attacker, then the attacker manages to predict the existence of the records with over 80% accuracy. Given any record, the attacker manages to infer manages to predict whether this record is used as in one of those training data sets. That is called the membership inference attack in horizontal federated learning. And the second one I'd like to introduce is extracted from our work, the class property inference attack. This is under the assumption that also there is a malicious client in the horizontal federated learning, but particularly it lacks the data of a certain class. In this example, we assume that bank C, it only contains information of negative customers. So then given black box access to the global model, if we build an attack model on the basis of bank C, then the attacker manages to infer the property of the certain data on the client, on other clients. Here, this certain data refers to the positive customers, which bank C is supposed to have zero knowledge of it because locally it doesn't have any positive customers. But in the end, the customer, the attacker manages to infer such information like the customers with loan equal to yes, also called the positive customers attribute has the income from 6K to 8K. And this violates the privacy preserving regulation of federated learning. About the inference attacks on vertical federated learning, I'd like to use this use case where the bank cooperated with a fintech company to build a vertical federated learning model. So the authors in this paper assume that there is a malicious attacker in the welfare system, and given white box access, which means the attacker knows the actual welfare model parameters. Then the attacker manages to infer such information. It can actually rebuild the columns on the features, which is stored on the fintech company. In this case, the white box access is kind of reasonable because the attack is embedded on the label holder, and there is a particular point in vertical FAL because usually this parameter server is held by this label holder because it needs this label information to needs this information together with the output of the vertical federated learning model to calculate the loss. So in this case, the purpose of vertical federated learning is to prevent the bank from knowing any of those features on the fintech company. But however, the attacker violates this privacy preserving regulation by inferring those features with very high confidence. So on the other way around, there is a label inference attack in vertical federated learning, which assumes that the malicious client takes place on the fintech company, and in the end, it manages to infer the labels of its customers, but this label is supposed to be private sensitive information that is unique for is stored on the bank side. So these are the several typical privacy attacks on the data synthesis technology and the federated learning system. The membership collisions attack and the property inference attack for data synthesis, and similar membership inference attack on horizontal federated learning, and the class property inference attack. And on vertical federated learning, there exists feature inference attack and label inference attack. Here I leave some open questions. First is how serious are those inference attacks from the financial services perspective? Second is what will the customers think about such privacy attacks? Because throughout all of those attacks, the original real data is not directly exposed to the attacker. The attacker are only conducting inference attacks there are still many constraints and limitations of such attack. So in the end, I'd like to ask, will such attacks hinder the deployment or development of synthetic data technology and federated learning technology? So that's the end of this presentation. Let's go to the discussion session. Any questions or comments? Jenna, from the business perspective, will such attacks have any serious impact?
I have one question is because I know like one of my colleague is working on that. Is the data reconstruction attack?
Yes, model immersion attack, I suppose.
It's the you didn't mention it, but I know like it works in the horizontal federated learning. I don't know if you ever like think about that in the vertical FL to do the data reconstruction attack.
Yes, so I only selected some typical examples of attacks. The data reconstruction attack also may work for the horizontal ones. But if such type of reconstruction attack is conducted on single machine learning model, then it is irrelevant to the federated learning process itself. Do you understand what I mean? So in the end, the federated learning manages to generate to produce a trained machine learning model. Then such kind of a reconstruction attack can be performed on this machine learning model to reconstruct the training data.
Yeah.
And this such attack is irrelevant to how it was trained.
Yeah.
So by introducing those attacks, I try to stick to the federated learning paradigm.
Hi, Han, it's Phil here again. Could I ask you about the first question that you asked, which is how serious are these interference attacks? Sorry. It's very difficult, I think, to get information from the financial sector as to the threat that they're under because of their effect upon their, what's the word I'm looking for? Their reputation within the market. If people feel that they're being breached or under serious attack, then it's going to undermine their reputation. So are you approaching this from a theoretical point of view, or are you aware of such attacks taking place? And if so, how many?
I don't think there are any real world cases of such attack. Because all those types of attacks are what I have seen in the most advanced literatures. And actually, those attacks requires very strict conditions and assumptions. For example, they need you need a malicious attacker from the server side or from the internal system of a bank. Sometimes you even need the white box access to the model. So that is not a simple attack that can be conducted by any staff in those banks. So overall, I don't think there are very serious cases, real world cases that where those such attacks has taken place. Actually, if we start from a good point by using such influence attacks, you can use it in a better way instead of the malicious way. For example, for the membership influence attack here, the attacker can infer whether a record has been used in the training data set or not. Actually, if this this technology is conducted by a good authority, then this authority can supervise whether those banks are abusing their customer data to train machine learning models. So that won't be a privacy risk. That would be some supervision approach. And also, for example, for the property inference attack, as I said, the attacker can infer the proportion of gender. But if this technology is controlled by a trusted authority, it can use this technology to supervise whether companies are using biased data sets to train the data generators. So it's those attacks are technologies. So it highly depends on who is using them. But in this presentation, I'm telling it is a privacy risk because as a cyber security researcher, we always have to think about the worst cases.
No, I think it's extremely encouraging, Han, that you're thinking about security in advance of problem actually existing, because it's usually the other way around, isn't it? It's usually once something has happened that these takes place. But it's interesting that you say that it's likely to be someone who is close to the organization, because a significant threat, particularly around operational technology, occurs from those within inside organizations. So we tend to think as cyber attack as an external threat, but a significant threat is internal to financial organizations.
Okay, thank you. Thanks for the question. Any other questions from?
Yes. So you said there are no current examples of these kinds of attacks, but if there were, would we know how?
Actually, it's if the attacker doesn't conduct any malicious approach after getting such a private information. For example, if you know that the customer data has been used in a training data set, then you probably know this record. For example, let's take the synthetic data attack as our example. Then if the synthetic data set is public, so if the attacker manages to infer which record belongs to the original data, then it knows this single record is a real record. So there is a real person who has such type of record, and it might be malicious. So I can't think from the criminal's perspective, but it might be utilized maliciously for fraud or something, cyber attacks. Yeah. I hope that answers your question.
Yes.
Any other questions? Okay, so if not, we can move to the end of this workshop. So through this workshop, we discussed some knowledge about federated learning and synthetic data. Both are supposed to be the advanced privacy preserving technologies. I got a more message here. Okay, so that's the end of this workshop.
Excellent. Thank you very much. My head is completely hurting now. A huge thanks to Dr. Han Wu and Dr. Zhong Zhao. Really fascinating presentations, at times way above my level of intellect, but that's really helpful. Thank you very much. So thank you to Newcastle University for putting this on, and also thank you to you for watching. We'll let you know when the slides and the video is available, usually through the usual channels. Okay, thanks very much.